Come on, join. Very good morning, all. Come on. Just revise kinematics. Good morning. I'll be back. चलिए Namaskaram सबको. Today I am going to discuss a very important topic, that is fluid dynamics. चलो. Shall we start? चलिए. Bhupatrao, brother of Bhupatrao. So, my dear students, in kinematics, what did we discuss? In kinematics, we talked about what is the velocity, what is the rotational component, what is the discharge, how much time it is taking, how much distance it is fluid has traveled. These things we have discussed, but we have not at all touched force. We have not touched force. So generally on a fluid element, I repeat, generally on a fluid element, the forces acting are, on a fluid element, the forces acting are pressure force Fp. Generally on a fluid element, I repeat, on a fluid element, the forces acting are pressure force Fp. Due to pressure there is a force, its own weight, that is gravity force. We have viscous forces due to viscosity, which in the first chapter I gave you the equation for F as mu a v by y. These are viscous forces. These are viscous forces. Okay, my dear students. So generally forces acting on fluid element are, I repeat, generally forces acting on fluid element are pressure force. It's something like this. इधर देखना, देखो, the fluid is flowing. Okay, now when the fluid is flowing and this fluid will exert a normal force on the wall, okay, there is a pressure force. For example, if I take, so this much weight is acting at this point, it's gravity, that is weight, and then when the fluid is flowing, there are shear viscous forces. So my dear students, generally the forces acting on fluid element are pressure force Fp, gravity and viscous force Fv. These are the, and in dynamics I'll be taking forces into consideration. In kinematics we have not touched force. Don't think that when we study kinematics there is no force on the fluid element. No, it is there, but we do not take into consideration. So in dynamics we'll be taking forces in our analysis. So generally forces acting on fluid element are pressure force Fp, gravity force Fg, viscous force Fv. On a fluid element, the dominant forces acting are pressure force Fp, gravity force Fg, and viscous force Fv. If we take all the three forces in our analysis, if we take all the three forces and analyze, it is known as Navier-Stokes analysis. So in Navier-Stokes analysis, all the three forces are taken into consideration. What are the three forces? Pressure force, gravity force, and viscous force. Now, let us neglect viscous force. Let us assume the flow. Let the flow be non-viscous. Let us neglect viscous forces. मान लो viscous forces are negligible. So if the flow is non-viscous, तो ये तो नहीं रहेगा. If the flow is non-viscous, if it is assumed to be non-viscous, this will not be there. When this is not there, you are left with only two. So when you take only these two forces and analyze, it is known as Euler's analysis. Now please tell me, in Euler's analysis, how many forces are taken into consideration? Two. What are those? Pressure and gravity. And in Navier-Stokes analysis, what are the forces taken into consideration? Pressure, gravity, and viscous. So now I'll go for Euler's equation. I repeat, now I'll go for Euler's equation. Okay. So you should tell me, my dear students, when I go to Euler's equation, which force is neglected? Viscous force. So when I derive Euler's equation, my first assumption will be the flow is non-viscous. My first assumption will be the flow is non-viscous. So let us derive Euler's equation. So already you have assumed in Euler's analysis, what is your assumption? Viscous forces are neglected. The flow is non-viscous. Chalo. The flow is non-viscous. Now I write Euler's equation. Assumptions. For every equation, assumptions play a very, very important role. For every equation, assumptions play. I request everyone to join on time. So please maintain discipline in life. Please try to join on time because you may be missing certain things. Do not attend from the middle. Okay, Euler's equation. My first assumption is, see, when I teach boundary layer theory, there I will be telling you the difference between ideal fluid, ideal flow. There is a clear-cut difference between ideal fluid and ideal flow. So in Euler's equation, the analysis that is made is the flow is flow. I'm not talking about the fluid. I'm talking about the flow. The flow is non-viscous. The flow is non-viscous. the flow is non-viscous. Flow के बारे में बता रहा हूं मैं. Flow. The flow is non-viscous flow. Very good, my dear students. Now, एक काम करते हैं. In kinematics, we have studied the acceleration in x direction is given by, already I taught you, and by this time I expect you to remember all kinematics equations. I had derived the equation for acceleration in x direction. The equation is u dou u by dou x, v dou u by dou y, w dou u by dou z, dou u by dou t. This is the equation for acceleration in x direction. You know that the acceleration vector is given by ax I cap, ay j cap, az k cap. Okay, no problem at all. Now, let us assume one-dimensional flow. That is, let us assume that the flow is occurring purely in x direction. Assume that the flow is taking place purely in x direction, something like this. So when the flow is taking place purely in x direction, there is no ay, there is no az. It is purely occurring in x direction. So there is no ay, there is no az. There is no ay and there is no az. So acceleration is given by axi. So if you want the magnitude of acceleration, so root of ax square, and that is equal to a. I repeat, my dear students, if the fluid is flowing purely in x direction, the total acceleration is nothing but ax. That is obvious. Now one more thing. The velocity vector is given by ui plus vj plus wk. If it is purely in x direction, there is no y, there is no z. So v is given by ui. And if you want the magnitude of velocity v, under root of u square, so v will be equal to u only. So listen carefully. If the fluid is flowing purely in x direction, if it is purely in x direction, there is no y, there is no z. Okay, so therefore I write this as there is no y, there is no z. So acceleration is given by ax. Why is acceleration given by ax? When it is flowing in x direction, there is no ay, there is no az, there will be only ax. So therefore this is the equation. And what is ax? What is ax? Look at ax is equal to, you have written here, what is ax? U dou u by dou x plus dou u by dou t. Because if it is purely in x direction, there is no y, there is no z. So ax can be written as u dou u by dou x plus dou u by dou t. So u dou u by dou x plus dou u by dou t. But my dear students, you know, if it is a one-dimensional x direction flow, u can be written as v. So acceleration is given by u can be written as v dou v by dou x. Dekho, u can be written as v dou v by dou x plus u can be written as v. So therefore dou v by dou t. Very good, my dear students. This is the acceleration. Excellent, my dear students. Ek baat suno. This is the equation when the fluid is flowing purely in x direction. Now let us assume that the fluid is flowing something like this. Let us take this as stream-wise direction. The fluid always flows along the stream-wise direction. Let us say it is stream-wise s direction. If it flows in x direction, it will be v dou v by dou x plus dou v by dou t. And if it flows in x direction, v dou v by dou x plus dou v by dou t. And if it flows in along streamwise direction, so what will be your equation? Very simple, my dear students. If it flows along the streamwise direction, now देखो एक बार, if it is in x direction, you got x. If it is streamwise direction, you get here s. So therefore, the acceleration along streamwise direction is v. देखो, if it is x direction, it will be x. If it is streamwise, it will be s. So therefore, v dou v by dou x. X के प्लेस में क्या लिखेंगे? Dou s plus dou v by dou t. This is the equation for acceleration along streamwise direction. And please note on that this is known as convective acceleration and this is known as temporal acceleration. If the flow is steady, this will be 0. If the flow is uniform, this will be 0. So acceleration has two components, convective and temporal. So now, please, my dear students, so I will write the acceleration along streamwise direction as v dou v by dou s plus dou v by dou t. This is one of the important equations already I had given in kinematics. Till now, is it clear, my dear students? अब ये I am going to use this equation. The streamwise acceleration is convective acceleration plus temporal acceleration. Please tell me, is this clear? If this is clear, then I'll proceed. It's a request to all of you. Please join on time because you will be missing concepts. Because I gave you something. Now you are joining, you don't understand. Then you start blaming teachers. Please, it's a request. All of you join on time. Okay. Now, please listen carefully. Now I write. The acceleration along streamwise direction is given by, just now I wrote, v dou v by dou s, dou v by dou t. Very good, my dear students. Now, look at, my dear students. Let us go to Euler's equation. Assumption. Can you tell me what is the assumption? Already I had told you. Please listen. In Euler's equation, we are not making an assumption of steady or unsteady. Please note down that. In Euler's equation, steady, unsteady assumption is not made. Only one assumption is made, that is, the flow is steady. That's all. The flow is steady. In Euler's equation, there is only one assumption made, that is, the flow is steady. The flow is steady. That is non-viscous flow. Non-viscous flow. Please, again, when I teach you boundary layer theory, there I will be telling you clear-cut difference between ideal fluid, ideal flow. Both are different. When he talks about ideal fluid, means he is talking about the nature of the fluid. When he is talking about ideal flow, he is talking about the flow nature, not about the fluid. So there is a clear-cut difference between both, which I'll be explaining to you very clearly. No problem at all. Now, let us try to derive Euler's equation. So please fix it in mind. What is the assumption? There is only one assumption made, that is, the flow, look at, what is that? The flow is non-viscous. Let us take a streamline. Can you tell me what is a streamline? What is a streamline? See, it is an imaginary line. When a tangent is drawn, that gives the velocity vector. इसका मतलब क्या है? All of you look at. Means this is the streamline. Listen, all of you, look at. So the flow is along the stream. देखो, the fluid is flowing along the streamline, along the streamline, along the streamline. The flow is always along the streamline. Means this is streamwise. So I write this as streamwise. Oh, the flow is non-viscous. I repeat, the flow is non-viscous. The flow is non-viscous. non-viscous. In Euler's equation, we never make an assumption of steady or unsteady. The flow is non-viscous. Absolutely fine. The flow is non-viscous. Chalo. Now, my dear students, let us assume that the fluid is flowing. देखो ऐसा flow हो रहा है. Fluid is flowing like this. This is all fluid. This is all fluid. This is all fluid. It is flowing. Let us take a fluid element. This is the fluid element. Please to know. Look at carefully. Let us assume that water is flowing. Let us assume that water is flowing. This is water. This is water. This is also water. But I have taken water. This is my fluid element. So I am analyzing the forces on this fluid element. It's something like this. In a class, there are some 50 students. So I take one student and analyze. So these are all students. These are all students. So I took one student. Arya, this is the fluid. This is also fluid. If water is flowing, ये भी water है. This is water. This is water. This is also water. But I took water. Certain element I took and I am analyzing forces. Very good. This is a streamwise direction. Okay, good. No problem. Let the length of this be ds. Can you tell me what is ds? It is the length of the fluid element that I am taking to analyze. Okay, let this area, assume that dA. Very good. So dA is the area of the fluid element. Now my question to you people is, can I calculate mass of the fluid element? Definitely I can calculate. Let the density of the fluid which is flowing be rho. Density is mass by volume. If you want mass of the fluid element, it is density into volume, or mass is equal to density. Can you give me volume of this fluid element? Volume is area. Area is dA and length is ds. Area is dA and length is ds. So therefore it is dA into ds. Area is dA, length is ds. So the volume is I repeat my dear students, इसका area dA है, length ds है, the volume is dA ds. So density into volume. So I got the value of mass, no problem at all. I got the value of mass, no issues. देखो एक बार. Now observe clearly. देखो एक बार, what is happening? This fluid, ये जो fluid है, this fluid will push it like this. This fluid will push it like this. So this is a normal force exerted by this adjacent fluid on this element. It's like this. मैं बता रहा हूँ सुनो. Listen carefully. It's like this. देखो, this is my fluid element. So actually this is all fluid. This is my fluid element. The bottom fluid will push it. When so it is exerting normal force on this area. This is dA. If the pressure is P, the force will be PdA. So when this is pushing, this will also push. When this is pushing, the adjacent element will cause a reaction in opposite direction. फिर से बता रहा हूँ सुनो. So this is the fluid. This is the fluid. It will push it. So if the pressure is P, it will be PdA. So when this is pushing, this element will push it. When this is pushing, this will cause a reaction in opposite direction. So what is a free body diagram? The diagram in Euler's assumption is no. Ashwin, I told you very clearly, I never made any assumption of incompressible in Euler. It may be compressible or it may be incompressible. I never made an assumption of incompressible. I simply made one assumption. What is that assumption? The flow is non-viscous. That's it. Please don't make your own assumptions. In Euler's equation, I made only one assumption. The flow is non-viscous. Apart from this, I never made any assumption. देखो एक बार. Now, look at. So this, if this pressure is P, यहाँ का pressure. अगर यहाँ का pressure P है, so it is P into area dA. So what is free body diagram? The diagram which shows forces acting on our element, So this will push. जब ये पुश कर रहा है तो when this is pushing, so this will push. When this is pushing, the adjacent element will cause a reaction in opposite direction. तो free body diagram क्या बताएगा? It shows forces acting on the element. So my dear students, कलर कौन सा ले लेंगे? यस, ये ठीक रहेगा. Yes. Let this be P into dA. Let this be P into dA. देखो एक बार, जब ये पुश कर रहा है, when this is pushing, this will push. When this is pushing, this will cause a reaction in opposite direction. Yes. Now देखो एक बार, let अगर यहाँ का प्रेशर P है, if it is P according to Taylor's expansion series, बताया था मैं, if the pressure is P here at a distance ds, I repeat my distance, if the pressure is P here at a distance ds, already I told you, if the pressure is P at a distance ds, it will be P plus dou P by dou S into ds. Hold on carefully. The pressure is varying only because the fluid is flowing like this. So the pressure is varying only along the streamwise direction. Only along the streamwise direction. I repeat, my dear students. If a father has two children, the total property will be equal to the property of son 1 plus son 2. But if a father has only one son, the total property is also equal to son's property. Now, the pressure is varying only in one direction, S, streamwise direction. So when the pressure is depending on only S, my partial will also be total. क्योंकि ना वो एक ही पैरामीटर पे डिपेंड हो रहा है, S. So when the pressure is varying only along the streamwise direction, क्योंकि the fluid is flowing like this, so pressure is varying only in streamwise direction. So it is a function of only one parameter. When it is a function of one parameter, my partial will also become total. So therefore, I will write this as P plus dP by ds. Why are you writing dou P by dou S as dP by ds? Because it is, if a father has one son, total property, total property is also equal to partial matlab son's property. But if the father has two children, then total property is this plus this. But here it is depending only on S, so partial will also become total. So therefore, dou P by dou S is dP by ds into ds. क्या होगा? It will be P plus dP. So I will write this pressure as P plus dP, and the area on which it is acting, let this area be dA. So therefore it is dA. Absolutely fine, no problem whatsoever, absolutely fine. And some students may be thinking, sir, why the pressure is increasing? देखो, sir, why you are writing plus dP? Why the pressure is increasing? I never said pressure is increasing. Simple logic. इधर देखो एक बार. So y is equal to x plus 5. Y is equal to x plus 5. Can I say that y is always greater than 5? Can I say that y is always greater than 5? No. For example, if x is 0, what is y? 5. It's not greater than 5. If x is minus 2, let us say x is minus 2, what will be y? So minus 2 plus 5 is 3, it is less than. So if x is 2, then y is 7. So all possibilities are there. What does it mean? If dP is positive, then the pressure will increase. If dP is negative, then the pressure will decrease. If dP is 0, pressure will remain same. So there are all possibilities. Do not get confused with just plus sign. Up to this, are we clear? Up to this, are we clear? Now, my dear students, ध्यान से सुनो एक बार. See, please observe carefully. The weight of this fluid element, I repeat, the weight of this fluid element will act in vertically downward direction. So the weight of this fluid element will act in vertically downward direction. So let this be the weight. Everyone knows weight is equal to mass into g. Everyone knows weight is equal to mg. So already mass is known. So weight is equal to m. What is m? Rho dA ds. That is m. This is m into g. Very good. So weight is equal to rho g dA ds. So this weight can be written as rho g dA ds. Absolutely fine. So एक बार देखना my dear students, एक बार देखना on the fluid element. देखो एक बार on the fluid element, what are the forces acting? This is pressure force. This is pressure force. This is gravity or weight. Actually, when the fluid is flowing like this, there will be shear. When the fluid is flowing like this, there will be shear. But you have assumed non-viscous. That's why it is not there. So please note down that in Euler's analysis, what are the forces coming into picture? Pressure force, gravity force. Pressure force, gravity force. Absolutely fine. No problem at all. No problem at all. No problem at all. Is it clear, my dear students? Is it clear? अब आगे बढ़ते हैं. Now, just now I gave you, देखो एक बार, I gave you what is the acceleration along the streamwise direction. Already आज आते हैं. Today's class, first I derived this because some people have joined late and they'll see like this, where from we got this equation. I had already derived in today's class. So it has two components, convective and temporal. Now acceleration along streamwise is v dou v by dou s plus dou v by dou t. So therefore, now observe here. Let us go for equilibrium. देखो एक बार, let us go for equilibrium. Can you tell me what is Newton's second law? According to Newton's second law, net force in the direction of motion is mass into acceleration. But please note down that it is flowing in what direction? Streamwise direction. So I write as acceleration along streamwise direction. Absolutely fine. Now let this make an angle. देखो एक बार. Let this make an angle theta. What is this? Our streamline is making an angle theta with vertical. So look at. Let us resolve. देखो एक बार. Let us take the equilibrium in the direction of flow. This is the direction of flow. These two pressure forces are in the direction of flow, but this is not in the direction of flow. So I will resolve this into two components. One is perpendicular to this direction of flow, one is parallel to the direction of flow. So देखो एक बार, let us draw this. To this streamline, this is perpendicular. So देखो, to this streamline, this is perpendicular. So this angle is 90. The total angle is 90, but this vertical is theta. The total is 90. This vertical is theta. So what will be this? 90 minus theta. So this angle is 90 minus theta. This angle is 90 minus theta. 90 minus theta. So देखना एक बार. So what are we doing, my dear students? 1 second, please. This weight is equal to rho g dA ds. So I will resolve this weight, this into two components. One is parallel to the stream, parallel to this flow, and one is perpendicular. So let us take this component. So the component of this in this direction is, देखो, can you give me this? Please understand carefully. देखो, इसका ये कौन सा कंपोनेंट है? अपोजिट. सो इफ इट इज अपोजिट, दिस विल बी साइन. इसका अपोजिट है तो द कंपोनेंट ऑफ दिस इन दिस डायरेक्शन इज अपोजिट. सो इसका साइन कंपोनेंट होगा. सो देयरफॉर रो जी dA ds sin. What is the angle? This angle is, what is this angle? 90 minus theta. Opposite. So this is 90 minus theta. So this will be rho g dA ds minus theta. It is cos theta. Absolutely fine. So please observe, my dear students. Now इसको भी यही कलर कर देंगे. देखो, now in the direction of flow, this is upwards, This is downwards, this is downwards. Let us take net force. Net force in the direction of flow is mass into acceleration. Mass into acceleration. Absolutely fine. One more thing. Let this be, what is the length of the streamline? What is the length of the streamline? Length of the streamline, it is ds. And with vertical, देखो एक बार, देखो इस streamline का vertical, this is streamline, vertical. What is this angle? Theta. So this is theta. Let us take this length as dz. Okay. What is cos theta? Anyone? What is cos theta? देखो एक बार, sin is opposite, but cos, what is cos? It is adjacent by hypotenuse, that is dz by ds. So therefore now I write, so ds cos theta is equal to dz, but everyone should be careful. What is dz? Z means vertical height. Z is vertical. In Euler's equation, Z stands for vertical, and S stands for streamwise. Now let us write the equation. Net force, so this opposite, this minus this, this minus this, that is the net force, is mass. Already mass is known, AS, already AS is known. What is AS? V dou V by dou S plus dou V by dou T. Here I write for your sake, AS is equal to V dou V by dou S plus dou V by dou T. Now let me write, my dear students, net force. देखो net force, this opposite minus, so that is the net force, is mass into AS is this. So therefore net force PdA minus P plus dP into dA minus, this is in the opposite direction, this minus. So therefore rho g dA ds cos theta. I repeat, my dear students, this minus this is also in the opposite direction, iska opposite, flow ke opposite, that's why minus. So what is this? Rho g dA ds cos theta. That is the net force. Net force should be equal to mass. What is mass? Mass is rho dA ds into acceleration. What is the acceleration? V dou V by dou S plus dou V by dou T. Absolutely fine. No problem whatsoever. Now I think इधर देखो एक बार, there is dA, both sides there is dA. Let us cancel it out. dA. So we are left with P minus dP, P minus dP minus rho g. Can you tell me what is ds cos theta? ds cos theta is dz. ds cos theta is देखो इधर, ds cos theta is dz. So I am writing this as dz is equal to rho ds into V dou V by dou S plus dou V by dou T. So therefore this P is gone. So finally we are left with minus dP minus rho g dz is equal to rho ds into V dou V by dou S plus dou V by dou T. Or you take these two to this side, तो क्या होगा? So it will be dP plus rho g dz plus rho ds V dou V by dou S plus dou V by dou T, and that is equal to 0. And this is one of the important equations, and this is your Euler's equation. And how did you get Euler's equation? By just applying Newton's second law. Can you tell me what is Newton's second law? It is net force is equal to mass into acceleration. This is Newton's second law. So Euler's equation is obtained by using Newton's second law along a streamline. Please, my dear students, is the equation, Euler's equation, clear? So while deriving Euler's equation, only one assumption is made. What is that? The flow is non-viscous. And 95% students, they don't remember this equation, but questions will come from this area. dP plus rho g dz plus rho ds into v dou v by dou s plus dou v by dou t is 0. That is very, very important. Very, very important. Where is G missing? Where is G missing? Aditya Sharma, where is G missing? Where is G missing? Yeah. Here I think. देखो रो जी लिया ना. Is it correct? Is the equation correct? Is there anything missing? But here net force is, देखो एक बार, net force is mass into acceleration. That's why I wrote mass. Net force is mass into acceleration. अरे यार weight term कहाँ है बोलो? Is it correct? अरे यार net force is not weight into acceleration, mass into acceleration. That's why I took mass. यहाँ पे already G is there. देखो, you said G is missing. I have taken G ना. I have taken G. इधर देखो, you said somewhere G is missing. Did I not take G? G लिया ना रे बेटा. And G is also there ना. देखो, G is also there. Is it correct? Now tell me, is it correct? अरे यार, Aditya Sharma, is it correct or not correct? See, after deriving so beautifully, you are asking something is missing. I've taken a lot of care. Is it correct? एक बार रिवाइज करना. Please एक बार रिवाइज करना. What is the assumption made while deriving this equation? Only one assumption is made. That is, the flow is non-viscous. Are Aditya Sharma, is it clear? And 95% of students, is it correct or wrong? You said G is missing. Are no one is commenting रे क्या हो रहा है? If it is clear, I'll proceed. Come on. Yeah. This is a wonderful equation. My dear students. It's a wonderful equation. चले चल एक सेकंड. आगे बढ़े. Is the equation clear? This is a beautiful equation, my dear students. But unfortunately, students don't remember this equation. I repeat, unfortunately, students don't remember. They just remember Bernoulli's equation. And today we'll be seeing the birth of Bernoulli's equation. So please fix it in mind. How many assumptions we have made while deriving Euler's equation? Only one. What is that? The flow is non-viscous. Chalo. And my question to you people is, can I apply Euler's equation for steady flow? Yes. Can I apply Euler's equation for unsteady flow? Yes. Because we have not made any assumption with respect to steadiness of the fluid. Therefore, Euler's equation is applicable both for steady and unsteady. But the only condition required for Euler's is the flow has to be non-viscous. Right. Now let's go to Bernoulli's equation. My dear students, Bernoulli's equation is obtained from Euler's equation. Again, I am telling you, Bernoulli's equation is obtained from Euler's equation. फिर से बता रहा हूं सुनो. We derive Bernoulli's equation from Euler's equation. So whatever the assumptions we make in Euler's equation, same will be there for Euler's equation also. Okay, assumptions. I repeat, my dear students. फिर से बता रहा हूं. Bernoulli's equation, today you will be seeing, it will be derived from Euler's equation. So as it is obtained from Euler's equation, so whatever assumptions are made in Euler, it will be there for Bernoulli also. First, what is the assumption you have made for obtaining Euler's equation? The flow is non-viscous. So that assumption will be there. The flow is non-viscous. Very good. Now I'll make second. देखो, in Bernoulli's equation, assumptions are very, very important. The flow is non-viscous. और एक बात. Now let us not waste time. आराम से देखो. Let us assume this to be a fluid element. Assume the fluid is flowing. During the course of its flow, when the fluid is flowing, in between the flow, जब flow हो रहा है, you are neither adding energy nor taking out energy. Means during the flow, no energy is added, no energy is taken out. फिर से बता रहा हूं सुनो. When the fluid is flowing, during the flow, no energy is added, no energy is taken out. Means what is that? It's something like this. You can imagine. Your parents have given you some money and they said मैं इतना दे रहा हूं, जाके कोचिंग कर लेना. बीच में कोचिंग स्टार्ट हुआ, बीच में आपको no one is giving money, no one is taking from you, so you have to move with its whatever you have. तो फ्लूइड को हम पता नहीं कब दिए, we have given some energy. Now after giving energy, अब वो फ्लो हो रहा है. फ्लो होते समय when I start analysis, in between the analysis, no one is supplying, no one is taking out, so it is flowing with its. तो आप बोलेंगे सर when no one is giving energy, how it is flowing? Already it has. So आपको हम पहले ही दे चुके हैं and we said आप बीच में नहीं देंगे, in between we don't give and you have to move with that. So when the fluid is flowing, in between neither the energy is supplied nor taken out from the fluid. So with its own energy, whatever it has, it is moving. So the beautiful second assumption is neither the energy is supplied nor neither the energy is supplied nor taken out from the fluid. And please note down that when I teach compressible fluid flow, there I will be using Euler's equation. Because while deriving Euler's equation, I have not made any assumption. In compressible flow. I never made any assumption of compressible, incompressible. Excellent, my dear students. Neither the energy is supplied nor taken out from the fluid. Third. Fourth. The fluid is flowing along the streamline. The flow is always along a streamline. the flow is, of course, this assumption is also there in Euler. Third assumption is also there in Euler. The flow is along a streamline. Everyone knows the fluid flows only along a streamline. Fourth and fifth. Keep quiet. Keep quiet. Let us take. My dear students, are the three assumptions clear till now? Whatever the three assumptions we have made, are they clear? Are they clear, my dear students? Are the three assumptions clear? Are the three assumptions clear? मैं बताता हूं, सुनो. See, Bernoulli's equation is taken from Euler's equation. So whatever assumptions we have made in Euler, they will be there even in Bernoulli. So in Euler you said the fluid is flowing along streamline. Here also it is along streamline. In Euler you said the flow is non-viscous. Here also the flow is non-viscous. And now I have made one assumption, that is neither the energy is supplied nor the energy is taken out. During the course of motion, during the flow, you are neither giving energy nor taking out. Okay. So I don't know what are fourth, fifth, but keep quiet for some time. Chalo. I wrote fourth and left a blank, and I wrote fifth and left a blank. So now tell me what is Euler's equation. याद है आपको Euler's equation? I said Euler's equation. By this time you are supposed to remember dP plus rho g dz plus rho ds into v dou v by dou s. Sorry. Dou v by dou t, and that is equal to 0. This is our Euler's equation. This is our, एक बार check करते हैं, is it correct or not? एक बार check करते हैं. V dp rho g dz plus rho ds v, yes, it is correct. It is correct. This is our Euler's equation. Absolutely fine. Absolutely fine. This is Euler's equation. Now, please understand, my dear students, all of you, listen. You know that if you see, this is actually your acceleration along the streamwise direction. Already I told you, this is acceleration. This this term is acceleration along streamwise direction. Acceleration along streamwise direction. And if you see, acceleration is a function of, एक बार देखना, it is a function of space s and time t. It is a function of space s and time t. That space can be x or y or z. So it is a function of space and time. So therefore it is a function of space and time. It is a function of space and time. Space and time. Look at. That's why. So the total property, देखो एक बार, total property is sum of partial properties. Now let us make one assumption. देखो, for the first time I am making one assumption. The flow is steady. The flow is steady. Can you tell me what will happen? Whenever the flow is steady, देखो, Euler's equation में we have not made steady assumption. In Bernoulli we are making assumption of steady. Be clear with your concepts. Euler's equation में हम steady का कोई शब्द use नहीं किए. But in Bernoulli I am using the word steady. Whenever the flow is steady, there is no change of property with time. In steady flow, there is no change of property with time. There is no change of property with time. So steady flow में क्या होगा? If the flow is steady, dou v by dou t will be equal to 0. Means now when, so I will write, in that case acceleration can be written as v dou v by dou s only. I repeat, earlier if it is not steady, it is a function of space and time. If it is steady, this will become 0. Steady may no change of property. This will become 0. When this becomes 0, now the acceleration is given by only this. Now I can say, when the flow is steady, acceleration is not depending on t. अब ये केवल किस पे depend हो रहा है? s. Now it is a function of space only. अब वो t पे depend नहीं होगा. So if a father has only one son, the total and partial will be what? Same. So now अब हम क्या लिखेंगे? dp plus rho g dz plus rho ds v dou v by dou s. Already it is steady. अगर वो steady है, this will vanish. अगर steady है, तो this will vanish. Now this will be equal to 0. Now tell me. Now the acceleration is depending only on space. When it is a function of only one parameter, whenever it depends only on one, then total and partial will be same. Now I can write acceleration as v dv by ds. If it depends on t, then I cannot write dv by ds. But now it is depending only on s. So this can be written as not dou v by dou s, but dv by ds, because it is a function of space only. So when it becomes ds, ये दोनों ds से खत्म हो गया, तो dp plus rho g dz plus rho v dv is equal to 0. So divide both sides with rho. So dp by rho plus g dz plus v dv is equal to, I am dividing with rho. So it will be 0. This is the equation. Very good. Now let us integrate this equation. I repeat, let us integrate this equation. So what do I get? Integral dp by rho plus integral g dz plus integral v dv, and integration of 0 is constant. Differentiation and integration are opposite. So what is the differentiation of constant? 0. What is the integration of 0? Constant. This is the one. Now I will make one more assumption. Please look at one more assumption. When can I take this rho out of the integration? When can I take rho out of the integration? I can take rho out of the integration only when rho is independent of pressure. But in compressible flow, my density depends on pressure. I cannot take it out. I can take rho out of the integration only when rho is independent of P. Rho will be independent of P. Rho does not change with P only when the flow is incompressible. So I will make an assumption of incompressible. Please look at the flow is incompressible. What do you mean by incompressible? Density is constant. So please note down that density is constant. So if I make that assumption, you can take rho bahar only when it is constant. Take it out. 1 by rho integral dp plus g is anyway constant, so bahar le lo, plus integral v dv is equal to constant. Please note down that if I do not make fifth assumption of incompressible, I cannot take this out. Already I made the assumption of incompressible, that's why I can take it out. So therefore, what is integral dp? Integral dp is p. So therefore, p by rho plus g. What is integral dz? Z. What is integral? What is x dx? X dx, x square by 2, and that is constant. So please note down that this is known as Bernoulli's equation. It's not Bernoulli's equation, it is known as classical. I will tell you what is ordinary Bernoulli's equation and classical Bernoulli's equation. It is known as classical Bernoulli's equation. Now please, before knowing the equation, you should know assumptions underlying or governing that equation. एक बार just to go through the assumptions. I request everyone to go through the assumptions. Please एक बार assumptions देख लेना. These are very, very important assumptions. I request everyone to go through assumptions. These are very, very, very important. Please tell me, is it clear? Is the derivation crystal clear? देखो देखो कितना साफ. One second, please. I'll attend one call. నేను ఏం చెప్పిన మహేష్ నీకు, నేను 10 వరకు క్లాస్లో ఉంటాను, 10 నుండి 12 వరకు రమ్మన్నా కదా నేను. నువ్వు అర్థమే కాదు మహేష్. నేను ఇప్పుడు క్లాస్లో ఉన్నాను, నేను 10 వరకు క్లాస్లో ఉన్నానని చెప్పాను కదా. ఒక పని చేయి, నువ్వు ఏం చేయకు, మళ్ళీ ఎప్పుడు వస్తుంది రావాలి నువ్వు ఎగ్జాక్ట్లీ. లేదు అంటే ఒక పని చేయి, 3 తర్వాత వస్తావా, ఈరోజు క్లోజ్ చేద్దాం. 3 తర్వాత వచ్చి మన ఏమంటారు, 3 తర్వాత వచ్చే ఇచ్చేసే అన్ని. ఓకే ఓకేనా, 3 తర్వాత తప్పకుండా రా. ఓకే ఓకే, బాయ్ బాయ్. Clear? Is it clear, my dear students? कितना neatly derive किया देखो. Clear all of you? नहीं होती तो रिजल्ट्स में क्या चेंज आता है सर? सेकंड assumption. हाँ, very good. If the second assumption is not made, what will happen? You know, when you are supplying energy, you have to add that energy. You have to add that energy. When you are removing energy, you have to remove that energy. And additionally, when I take up, yes, definitely, I will take up your question, Mr. Dheeraj, who asked that question. So I'll take up that question, so you don't have to worry. So whenever this second, neither energy is supplied nor taken out. If you supply, you have to add that also. If you supply, you have to add that also. So therefore, so don't worry, it will be taken care. It will be taken care. Do not worry at all. It will be taken care. Okay na? Chalo. It will be taken care. It will be taken care. Okay? Right. Chalo. Aage bade. See the beautiful equation, my dear students. See the beautiful equation. Wow. What a beautiful equation. What a beautiful equation. This is known as classical Bernoulli's equation. All of you, is the derivation clear, Re Baba? You are not like, there is no enthusiasm in you. I'm worried about your enthusiasm. Really, I'm worried about your enthusiasm. Simply, no comments, nothing I say. It's not correct. That is not the way of learning. You should be highly energetic, enthusiastic. You should have that inquisitiveness to learn. Absorb, absorb, absorb. So, yaad rakh lena. You should remember both. What are those both? Bernoulli as well as Euler's equation. But unfortunately, see, when we go to laminar flow, we'll be talking about that. Abhi nahi. Abhi Navier Stokes mein to viscous forces aayega. So abhi Sonupriya ji, we are not taking viscous forces into account. I'll be taking a little later viscous forces. I repeat, till now we have taken only 2 forces, that is pressure and gravity. So when I include viscous forces, there will be seeing how all the things are coming. Don't worry. In laminar flow, you'll be seeing the beauty of that. In laminar flow, you'll be seeing the beauty of that. Right now, we are not touching. I told in Navier-Stokes equation, viscous forces is also involved. But what is the assumption you have made? Non-viscous. So, for some time. Is it okay? Is it okay, Sonu ji? Okay, chalo. So now we'll move to, now we have to analyze thoroughly. So is this equation clear? And please don't say Bernoulli's equation, Bernoulli. And you should use the word classical.
We'll talk about what are the other equations of Bernoulli. Classical. Okay, now, chalo. 8 seconds. Someone is calling. We'll switch it off. Yeah. Okay, good. Ab dekho. But please fix it in mind. Please fix it in mind. What are the assumptions? Please fix it in mind. What are the assumptions? What are the assumptions? What are the assumptions? What are the assumptions? First, non-viscous flow. Non-viscous flow. Second, I repeat, first is non-viscous flow. Second, I repeat, first is non-viscous flow. Second is the flow is along streamline. Third is neither the energy is added nor removed. Fourth, the flow is steady. And fifth, look at, fourth, the flow is steady. And fifth, the flow is incompressible. Please note down that Euler's equation can be applied for compressible as well as incompressible, steady as well as unsteady, but Bernoulli's equation is applicable only for steady incompressible. Bernoulli's, please see the difference clearly. Please see differences clearly. Euler's equation can be applied for compressible or incompressible, steady or unsteady, but Bernoulli is applicable only for steady incompressible flow. Chalo, let's take up that equation. So whatever I had derived, देखो P by rho plus G dz plus V square by 2. Excellent. P by rho plus V square by 2 plus Gz. Let us analyze this equation. Let us analyze this equation. Okay, suno. My dear students, let us see the unit of each quantity. I repeat, एक quantity का unit देखेंगे. And when you are adding something and subtracting something, equating something, all should have same units. When you are adding, subtracting, equating, for example, mass को mass ही add करेंगे 3 kg plus 2 kg, or from mass you can remove mass only. You cannot add mass to power. So when I am adding something, this quantity, you are adding must have same unit. Let us check the unit. देखो एक बार V square by 2. Let's see the unit. Please listen. Can you tell me what is kinetic energy? The kinetic energy is given by half mv square. So can I write this as kinetic energy by mass is equal to V square by 2? Yes, I can write. Similarly, please note down that when I derived, I told very clearly एक बार derivation देखना. See my dear students, एक बार derivation देखना. What is Z? देखो, Z is vertical. So Z is vertical. So therefore, now I write the potential energy is given by mgz. The potential energy per unit mass is equal to gz. Means each quantity is representing, I repeat, means each quantity is representing. देखो, what is gz? Gz, energy per mass. Which energy? Potential energy per unit mass. What is V square by 2? Kinetic energy per unit mass. Means each term is representing energy by mass. Of course, potential energy by mass. Energy by mass. Of course, kinetic energy by mass. Energy by mass. Of course, pressure energy per unit mass. So in this equation, each term is representing energy of the fluid per unit mass. Each term is representing energy of the fluid per unit mass. Each term is representing energy per unit mass. So potential energy per unit mass, kinetic energy per unit mass, pressure energy per unit mass. So now I can write, देखो एक बार, the sum का मतलब addition of pressure energy per unit mass, kinetic energy per unit mass, pressure energy, potential energy per unit mass is constant. It is saying something like this plus this plus this is constant. This plus this plus this is constant. Means when something is constant, we say conserved. We say conserved. तो एक काम करो आप, you multiply both sides with mass. तो क्या होगा? m into p by rho plus mv square by 2 plus mgz. You multiply for this equation. In this equation, you multiply both sides with mass. So mass into constant. My dear students, mass is constant, this is constant. Constant into constant is new constant. So I can write pressure energy. So इसको ऐसे लिखेंगे. Pressure energy plus kinetic energy plus potential energy is constant. Whenever something is constant, we call it as conserved. Conserved. What does it mean? During the flow, this may increase, so this may decrease, so that the total is constant. That is known as conserved. So Bernoulli's equation is representing conservation of energy. That's why it is known as law of conservation of energy. I repeat, my dear students, Bernoulli's equation is known as conservation of energy. Conservation of energy. तो यहाँ पे अब लिख रहा हूँ मैं. Now I'll write Bernoulli's equation. Now I write, देखो एक बार. Now I write Bernoulli's equation. So in brackets, conservation of energy. Why? Because this plus this plus this is constant. Now I'll give you the statement of Bernoulli. देखो, I'll give you Bernoulli's statement. What is the statement? देखो, and now I'm giving you the statement. In ES, he may be asking, state Bernoulli's theorem. What is that? Let's see. It says, in a steady incompressible flow, see, for Bernoulli you have already made steady and incompressible. In a steady incompressible flow along a streamline, the sum of pressure, kinetic and potential energy is constant. In a steady incompressible and in a steady incompressible flow, in a steady incompressible flow along a streamline, when no energy is supplied or taken out, the sum means addition, the sum of pressure, kinetic energy and potential energy is constant, and that's why Bernoulli's equation is known as conservation of energy. Conservation of energy. So this is very, very important, my dear students. Bernoulli's statement you have seen clearly. So P by rho plus V square by 2 plus क्या था वो GZ ना? Let me check that equation. P by rho plus V square by 2 plus GZ is constant. Can you tell me the unit of each quantity? In this equation, each term has a unit of what? Energy per unit mass. So in this, my dear students, in this equation, each term has energy per unit mass. In this equation, Each term has the unit of energy per unit mass, that is joule per kg, joule per kg. So you know clearly. Now what we do is, let us take the same equation, energy per unit mass. M का मतलब mass, M is mass, M is mass. This I write as P by rho plus V square by 2 plus GZ is constant. So what I do is, to this equation, I'll divide both sides. This is the left hand side, this is the right hand side. I'll divide both sides with G. What do I get? Let's see. Divide with G, divide with G, divide with G, divide with G, divide with G. You know, G is constant. Constant by constant is a new constant. So this G is gone, and rho G is W. So therefore, now I write energy mg. What is mg? Weight. What is mg? Weight. So P by W plus V square by 2G plus Z. देखो एक बार, P by W, rho G is W plus V square by 2G plus Z is constant. And this is the other form of Bernoulli. Can you tell me what is the unit of each quantity? If you see each quantity in P by W, V square by Z, energy per unit weight. In this it is energy per unit mass. In this it is energy per unit weight. Very good, my dear students. So from now onwards, I will be using this equation predominantly. इसको मैं बहुत use करूँगा. P by W, where W is specific weight of fluid, which is rho G. In first chapter we have seen P by W plus V square by 2G plus Z is equal to constant. Now let us see the significance of each term. Let us see the significance of each term. Each term का significance हम देख लेंगे. Okay ना? चलो. Let's see the significance of each term. My dear students, till now is it clear? Till now is it clear? If it is clear, then I'll move ahead. Till now is it clear? बोलो बोलो बोलो. Clear? Wow. Okay. Very good, my dear students. Now, we'll take up this equation and move ahead. We'll take up this equation and move ahead. I'll take up this equation and move ahead. Okay. So, P by W plus V square by 2G plus Z is equal to constant. Okay, let us take up this equation and we'll proceed, my dear students. Chalo. Now, let's do neatly. Don't worry. Let us do it any things in a. Now, one more thing. What is Z? And you told, my dear students, each term in this equation, each term is representing energy per unit weight. Energy is written as joule. Joule means Newton meter. Energy is, this is Newton meter. Newton meter means joule. Weight is in Newton. अरे यार, energy is in Newton meter joule. Weight is in Newton. Newton कट गया. So it is meter. So please note down that each term is representing energy per unit weight, but that can be written as meter. Meter. So this meter is known as head. For the first time I am introducing the word head. This is known as head. This I call it as pressure head. This I call it as velocity head or kinetic energy head. This I call it as potential energy head or datum head. Let us see the significance of each term. What does each head represent, I repeat, P by W is known as pressure head, V square by 2G is known as velocity head or kinetic energy head, and Z is known as potential energy head or DATUM, datum head. So according to Bernoulli's theorem, the sum means addition, the sum of pressure head, kinetic energy head and potential energy head is constant along a streamline when no energy is supplied. That should be kept in mind. So when I am applying Bernoulli's equation, neither the energy is supplied nor taken out. Okay. Now understand carefully. Significance of, or the physical meaning of, physical significance of each head. Physical significance of each head. Physical significance of each head. First we'll talk about pressure head. P by W is pressure head. P by W is pressure head. Let us say what is pressure head. Let us take a pipe. Through this pipe, say the fluid is flowing. There is a pipe, I have taken a pipe, and through this pipe the fluid is flowing. Let us connect a piezometer. Let us connect a piezometer. Understand carefully, the flow is purely in X direction. I repeat, my dear students, the fluid is flowing purely in X direction. When it is flowing purely in X direction, there is no role of velocity in the perpendicular direction. फिर से बता रहा हूं सुनो. You don't find any component in perpendicular direction. So if the fluid, for example, you are moving in, देखो, एक सेकंड में बताता हूं. देखो एक बार. We are sliding this. We are sliding this. Purely it is moving in X direction. How much distance it is covering in Y direction? 0. देखो एक बार. Purely it is in X direction. Purely it is in X direction. देखो. So whenever it is purely moving in X direction, there is no component in the perpendicular direction. So therefore it cannot have any velocity in the perpendicular direction. So therefore, मुझे बताओ, if the fluid is flowing purely in X direction, what is the role of velocity in Y direction? No role at all. In perpendicular direction. Now, if you understand clearly, the liquid is rising. देखो एक बार. The liquid, this is the liquid. This is the liquid. Now the liquid is rising. Let it rise up to this height. देखो एक बार. Yeah. Let it rise up to this. Now my question to you people is, even though the liquid is flowing purely in X direction, there is no velocity in the perpendicular direction. But why is the liquid rising? Can anyone tell? Even though there is no role of velocity in perpendicular direction, why is the liquid rising in the perpendicular direction? It is not because velocity. There is no velocity in this direction. देखो. In this. So it is not rising due to velocity, but it is rising due to pressure. It is rising due to pressure. Let it rise, let us say, up to a height h, whatever it may be. Let it rise up to a height h. Or, okay. So if you want pressure here, देखो एक बार, if you want pressure here, What is the pressure? Now, देखो, this is the, look at carefully. This is the flowing fluid and this is a static fluid. This fluid is flowing. This is not flowing. So I will apply hydrostatic law to this fluid. To this. This is the flowing fluid. I am not applying hydrostatic law to this. This is the flowing fluid. This is static fluid. So let me apply hydrostatic law. You know very well. And if the pressure is P here, at any depth h, the pressure is given by, at any depth h, so from this, यहाँ पे, at any depth h in your pressure measurement you have studied, at any depth h, the pressure is given by rho gh, where rho is density of this fluid. So therefore, now I write h is equal to P by rho g, or h is equal to P by rho g is W. इसका मतलब क्या? Yes, इसका मतलब क्या है? What is the meaning of this? Whatever the liquid is rising in the piezometer, it is purely due to pressure. So pressure head means what? Pressure head means what? Don't do anything. The fluid is flowing like this. Idhar dekho. Look at my distance. The fluid is flowing like this, in this direction. So in this direction, there is no role of velocity. The fluid is flowing. Whatever the height it is rising due to pressure, that height is known as pressure head. If someone asks you what is pressure head, the height by which the liquid or the fluid rises due to pressure is known as pressure head, and that is given by P by W. So if the pressure is more, the liquid will rise to greater height. If the pressure is less, the liquid will rise to a smaller height. So pressure head is given by P by W. अगर आपको इंटरव्यूज में कोई पूछेंगे, if someone asks you what is pressure head, your answer should be what? Your answer should be what? So it is the height by which the liquid rises due to pressure. All of you, are we clear? Whatever the height the liquid is rising due to pressure, it is pressure head. So kuch mat karna. Say the fluid is flowing in x direction, in this direction. Connect a piezometer here. Connect a piezometer. It is flowing. So whatever the liquid is rising, let us say it is rising up to this level, and that is known as pressure head at this point. Pressure head at this point, at this point, at this point. So due to pressure, जो भी rise हो रहा है, it is pressure head, pressure head, pressure head. Now we have seen the first head. What is first head? Pressure head. So I will write pressure head as the height through which the fluid rises due to pressure is known as pressure head. Pressure head, pressure head. Very good, my dear students. Excellent, excellent. Now we'll go to the second head. Now we'll go to the second head, that is velocity head or kinetic energy head. 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 Kinetic energy head. Velocity head or kinetic energy head. Okay, no problem at all. Velocity head or kinetic energy head. देखो, it is given by v square by 2g. What does it mean? Let us see. What does it mean? Let us see, my dear students. Let us take a fluid element. Say this is our fluid. Say, मान लो this is the fluid. Imagine this to be a fluid. What is its initial velocity? It is at rest now. It is a fluid. What is its velocity? 0. Now look at carefully. Now you drop freely falling. You drop this in a frictionless environment. Air resistance. There is air resistance. Let us neglect this air resistance. It is, मान लो ये air कोई resistance offer नहीं कर रहा है, frictionless. You drop that fluid in a frictionless environment. Let us assume that it is falling through this height. Let us assume that, अरे बाबा, अब देखो, it is falling. So let us say it is falling from this height to this height. चलो, अब देखो, let the velocity here be v. अरे यार, it is falling, really falling. Let the velocity here at this point be v. Let the velocity here, यहाँ का velocity, यहाँ का velocity, let it be v. यहाँ का velocity, let it be v. यहाँ का velocity, let it be v. Okay, no problem at all. No problem at all. देखो एक बार, यहाँ का velocity v. Okay, no issues at all. Good. एक बात बताता हूं, g को 10 ले लें. Let us take g as 10. Let us take g as 10. Okay ना? Okay. अब देखो, easily I'll tell you. g को 10 लेंगे तो 20 होगा 5. Let this be equal to 5. एक सेकंड सुनो. तो what will be your v? What will be your v? V square. Let us take g as 10. 2g into 5, or v square is equal to 2 into g is 10. Let 9.81. अरे calculation के लिए 10 ले लेंगे. I know 9.81, but for easy calculation, let me take it as 10. So कितना होगा? 20 into 5 is 100. अरे यार, v square is 100. So v is equal to what? Root 100. So that is equal to what? 10. अब देखना. What is the velocity? 10. And how much height it has fallen? It fell through a height of 5 meters. अब ध्यान से सुनो. What is velocity head? To reach this particular velocity of 10 meter per second, इतना velocity reach करने के लिए, इतना velocity reach करने के लिए कितना 10, कितना height fall कर रहा है. इस velocity को reach करने के लिए whatever the height it is falling, उसको हम बोलते हैं velocity head. In this case, तो 10 मीटर पर सेकंड के लिए हमारा हेड होगा 5. What does it mean? To reach a particular velocity, through what height the liquid is falling in a frictionless environment, and that is known as velocity head. मतलब एक पर्टिकुलर वेलोसिटी रीच करने के लिए, इन दिस केस कितना वेलोसिटी रीच कर रहा है वो 10. इन दिस केस कितना रीच कर रहा है 10. तो 10 वेलोसिटी रीच करने के लिए कितना हाइट फॉल कर रहा है. टू रीच 10 मीटर पर सेकेंड, हाउ मच इट इज फॉलिंग, एंड दैट इज नोन एज वेलोसिटी हेड. व्हाट इज द डेफिनेशन ऑफ वेलोसिटी हेड? It is the height through which the fluid falls in a frictionless environment freely to reach a particular velocity. For example, what is the initial velocity? 0. इधर देखना, देखो एक बार. Now it is falling. Let us assume that it is falling through 5 meter. तो 5 meter fall करने किया तो कितना velocity reach किया? 10 मीटर पर सेकेंड. So 10 मीटर पर सेकेंड का velocity head होता है 5. So the velocity head of 10 meter per second is 5. What does it mean? To reach 10 meter per second, initially the velocity is 0. To reach 10 meter per second, यहाँ पे it is reaching 10. So to reach 10 meter per second, what is the height it is falling in a frictionless environment? That is known as velocity head. So it is the height through which the fluid falls in a frictionless environment to reach a particular velocity. All of you, have you followed? My dear students, have you followed? My dear students, have you followed, beta? अरे बोलो रे. I'm asking a question, waiting for your responses. Is it clear? Is it clear? All of you. Not clear, not clear, not clear. Yes, sir. अरे यार, respond. Jakan Baba Jakan. Jakan Baba.
Baba Jakan. Arey Baba Jakan. Very good. Isa Teja. Isa Teja. Teja Isa. Isa Teja. Teja Isa. Okay. Chalo, let's proceed. Now we'll go to the next head, that is potential energy head or datum head. Potential energy head. It is very simple, my dear students. It is very simple. Ariyar, there is some fluid here. Some fluid. Let us assume that whenever you are measuring energies, you should always measure with some reference line. For example, there are two bodies, let us say. Ariyar, when you are measuring potential energies, you will be measuring with some reference line. So if, for example, there should be some reference. For example, there is a body here, there is a body here. 1 and 2. I say, dekho ek baar, I say the potential energy of this is 0. I also say the potential energy of this is 0. Then someone says, are you fool? Then I say, for this I have taken this as the reference. For this I have taken this as the reference. How can the potential energy be 0? दोनों को compare करेंगे तो definitely इसका potential energy इससे ज़्यादा है compared to the second one. The first one has more potential energy. So therefore you need some reference. So you need to measure with some reference. That reference from where you are measuring energies is known as datum. Datum means reference. From reference, whatever the vertical height you are taking, from reference, whatever the vertical height you are taking, that is known as potential energy head or datum head or reference head. Is it clear, my dear students? So therefore, P by W, pressure head, kinetic energy head plus datum head is known as total head. And I will be talking about piezometric head a little later. Don't worry. Sir, to piezometric head बताए नहीं fluid mechanics में. Don't worry. When I talk about a little later, I'll be talking about this piezometric head also. Very good, my dear students. Awesome. No tension at all. Till now, I expect it is clear. I feel that till now it is clear. I personally feel that till now it is clear. Is it clear? Okay, now? Very good. Let's proceed, my dear students. Look at. Now, please understand. Let us take a horizontal streamline. Let us take a horizontal streamline. Now, whatever I am going to discuss, it is very important. Whatever I am going to discuss, it is very important. So, it's something like this, my dear students. There is a pipe. Through this pipe, the fluid is. There is a pipe. Through this pipe, the fluid is flowing. The fluid is flowing. So if you take a streamline, it is something like this. So I will take up horizontal streamline. That is the meaning. So another streamline like this. Another streamline. These are horizontal streamlines. Okay. Let us take horizontal streamline. Now, एक second. Before we go to this, now, let us take a streamline like this. Okay. You have seen Bernoulli's equation. In Bernoulli's equation, the flow is along a streamline. So if you want to apply Bernoulli's equation, you should apply along a streamline. If you want to apply Bernoulli's equation, you should apply along a streamline. along a streamline, okay. Let us take 2 points, point 1 and point 2. Where are these 2 points? They are along on the streamline, okay. देखो, let this be Z1. Can you tell me what are Z1, Z2s? They are from the reference. You are measuring from this reference. From the reference, the potential head of 1, potential head of 2. Let the velocity at 1 be V1. Let the velocity at 2 be V2. I told you very clearly, along the streamline, velocity may be constant, may be changing. Okay. Let the pressure here be P1. Let the pressure here be P2. Just now you saw P by W plus V square by 2G plus Z is equal to constant. Just now you saw P by W plus V square by 2G plus Z is equal to constant. Okay, no problem at all. No problem at all. No problem at all. Okay, fine. Listen carefully. Dekho. You know, if PV is constant, then I can write between 2 points P1 V1 is equal to P2 V2. Absolutely fine. There is no problem in that. There is no problem. Similarly, if the summation of this is constant, iska matlab hai, the value of this at 1 is equal to value of this at 2. It's something like this. Okay, P1 by W. I am applying this to 0.1. What do I get? Pressure head at 1. So I am not writing W1. Why are we not writing W1? You know, W is equal to rho G. G is anyway constant. But in Bernoulli's equation, one of the assumptions is incompressible. So density is constant. Whether it is 0.1 or 0.2, density is constant. Therefore, rho 1 is rho 2. Therefore, I am not writing W1, W2. W is constant because it is incompressible. No problem at all. So P by W plus V1 square by 2G plus Z1. Let us say its value is some 10. Say some 10. Similarly, clearly he said this total value is constant. So what will be the value at 0.2? It will also be 10. So therefore I write P2 by W plus V2 square by 2G plus Z2. That is at 0.2. That is at 0.2. So as it is constant, so it has to be constant. This is 10. This is 10. So therefore, now I write this. This is the Bernoulli's equation for ideal fluid. What do ideal flow? I'm sorry. Ideal fluid flow. Ideal fluid flow. The fluid is not ideal. Ideal flow. Flow. What do you mean by ideal flow? Frictionless, non-viscous. See, please note on that. In Bernoulli's equation, he is not talking about the type of the fluid. He is talking about the type of the flow. So the flow is non-viscous. Okay, koi baat nahi. Now listen. Listen, my dear students. This is the equation. This is the equation. So this is the Bernoulli's equation between 2 points along the streamline. Between 2 points along the streamline. Now let us take horizontal streamline. Let us take horizontal streamline. This is the streamline. Let us take horizontal streamline and let's take 2 points. Let us take 2 points. Let this be Z1. Let this be Z2. If it is horizontal, can I write Z1 is equal to Z2? अरे बाबा, अगर horizontal है, there is no change in potential energy. Z1 is Z2. So when Z1 is Z2, my classical Bernoulli's equation takes the form something like this. Z1, Z2 are same. So my equation will take the form P1 by W. Wait, please. Disturb किया. Sorry. या अब देखो P1 by W देखो प्लस V1 स्क्वायर by 2G प्लस Z1 is equal to P2 by W plus V2 square by 2G plus Z2. Okay, but if it is horizontal, Z1 Z2 are same, so therefore let us cancel Z1 Z2. So the equation will take the form P1 by W plus V1 square by 2G P2 by W plus V2 square by 2G. This is the equation. Very good. This is the equation. Now observe carefully. The sum along the horizontal streamline, the sum of pressure and kinetic energy is constant. इसका मतलब क्या है देखो एक बार. It's a simple logic, my dear students. You have two bank accounts. Let us say bank A, bank B. Something like this. I'll put it like this. एक second. Punjab National Bank, Vijaya Bank. Something like pressure and velocity. Punjab National Bank, Vijaya Bank. In Punjab National Bank, you have 8 lakhs, and in Vijaya Bank, you have 4 lakh. No one is supplying, no one is taking out. What will be your total? 12. Now, what I have done is, after some time, I had transferred 3 lakhs to this. So 3 lakh इसमें transfer किए. When I transfer 3 lakhs, when I transfer 3 lakhs from here to here, so 3 lakhs निकाल दिए, it will be 5. So 3 will be added to this 7. It is 12. What does it mean? The total is constant. Pressure may change to velocity or velocity may change to pressure, but the total will be constant. देखो, see, if this is decreasing, when 8 is becoming 5, my 4 is becoming 7. When 1 is decreasing, other should increase. When 8 is becoming 5, 4 is becoming 7, total is 12. So in horizontal streamline, along the horizontal streamline, if pressure decreases, agar pressure decrease ho raha hai, listen carefully, if pressure is decreasing, velocity should increase, or if pressure is increasing, velocity should decrease. So in a horizontal streamline, so observe here, during the flow, for example, flow हो रहा है, तो compare 1 2, अगर यहाँ पे pressure P1 P2 है, if the pressure is decreasing, then velocity should increase, vice versa. Or if velocity is decreasing, pressure should increase. अरे बाबा, are we clear? All of you, are we clear? अरे बाबा, are we clear? It's like this. When pressure is in a horizontal streamline, when pressure is increasing, velocity decreases, or when velocity is increasing, pressure decreases. Please look at my dear students. Now, I will show you a beautiful, I'll experiment. Now, अभी मैं एक experiment करूँगा, so that you can visualize clearly. So, my dear students, P1 by W plus V1 square by 2G is equal to P2 by W plus V2 square by 2G. Okay. What is this? If velocity is increasing, let us say V1 is 5, V2 is 10. What is happening? Velocity is increasing. You tell me, if V2 area, this plus this is equal to this plus this. If this is increasing, velocity is increasing. When velocity is increasing, pressure should decrease. When velocity is increasing, pressure should decrease. So definitely P2 is less than P1. All of you are be clear? All of you are be clear? अब देखो मैं आपको एक एक्सपेरिमेंट करके दिखाऊंगा. Don't worry, my dear students. Look at, my dear students. Look at. So I am doing an experiment. Let this be horizontal. Now tell me, what is the pressure here? What is the pressure at the top? Atmospheric. What is the pressure at the bottom? Atmospheric. Because pressure is normal. So I have taken a piece of paper. So like this. So here the pressure is atmospheric. Here the pressure is atmospheric. Very good, my dear students. एक बार देखना. We'll do it very clearly. Okay, this is the paper. Horizontal, held horizontal. देखो एक बार, horizontal. So what is the pressure at the top and bottom? At the top it is atmospheric. At the bottom also it is atmospheric. Look at, this is a paper. At the top it is atmospheric. At the bottom it is atmospheric. So now what I do is I will blow air, मतलब ऊपर का velocity बढ़ाऊंगा. When I increase the velocity, I look at नीचे I'm not touching below. Initially, before blowing, the pressure is atmospheric, the pressure is atmospheric, the pressure is atmospheric, the pressure is atmospheric. Now I'll blow. Air को flow करेंगे. देखो, I will increase the velocity. If I increase the velocity, अब देखना ये pressure घट जाएगा. कैसा घटेगा? So, if please understand carefully, when air is not blowing, when we have not blown the air molecules are getting sufficient time to cause normal force on this. I repeat, my dear students, when इसको एक काम करते हैं. Don't worry. Now, let us take the second case. Now, we will blow air at the top. So, look at, when I am blowing the air is moving faster. When air is moving faster at the top, it is not getting time. Wait. When air is moving fast, इतना fast जा रहा है. So it is not getting time to exert normal force. So pressure क्या होगा? कम हो जाएगा. I repeat, my dear students, it's something like this. So if I am increasing the velocity, it is not getting time to exert normal force. That's why the pressure is decreasing. So if the velocity is less, देखो, now please understand carefully, clearly. Air molecules, atmospheric air, it is getting sufficient time to exert this force, that is pressure. If my fast blow करूंगा, it is moving like this. So it is not getting time to exert this normal force. That's why the pressure is decreasing. I repeat, when air is flowing faster, the molecules are not getting time to exert force in this direction. So pressure is decreasing. All of you, have you followed? I repeat, my dear students, why the pressure is decreasing with increase in velocity? When the velocity is increasing, so if the air is moving faster, actually pressure is normal force. Let us say it is not moving, air is not moving faster, let us say. So when it is not moving faster, it gets time to exert normal force, so there is a sufficient pressure. But if air moves faster, pressure is normal to the surface. If it moves faster, it is not getting time to exert this force, therefore pressure is decreasing. So क्या होगा? So when air is moving, initially it is like this. This is case 1 and this is case 2. Now, when air is moving faster, तो क्या हो रहा है? When air is moving faster, it is not getting time to exert normal force. जब ये fast flow हो रहा है, so it is in this direction, it is moving faster. When it is moving faster, when velocity is increasing, pressure is decreasing, pressure is normal. So it is not getting, molecules are not getting time to exert normal force. So therefore, what is happening? This pressure is less than atmospheric pressure. So this pressure is more, this pressure is more, this is less. So the paper will get lifted up. The paper will get lifted up. The paper will get lifted up. अब देखना, एक बार देखना. Look at my dear students. All of you listen. देखो एक बार. So I am blowing air. Oh my God. Oh. देखो. When the velocity is increasing, it is not getting sufficient time. When the velocity is increasing, it is not getting sufficient time to exert pressure. So therefore pressure is decreasing. When pressure is decreasing, bottom pressure is more. Therefore it is lifted up. देखो, bottom I am not touching. ये देखो. Oh. देखो एक बार. Please see. अरे. When the velocity is increasing, the pressure is decreasing. When this pressure is less, this pressure is more, it will get lifted up. This is a beautiful example of Bernoulli's equation. As the velocity is increasing, the pressure is decreasing. And due to pressure difference, it is getting lifted up. Are we clear? All of you, are we clear? बोलो रे. Clear? Great. So this is the live example of Bernoulli. So this is कभी नहीं भूलेंगे ना, याद आया जाएगा. Very good. Thank you. Okay, चलो अब आगे बढ़ते हैं. Now we'll proceed. Listen carefully. Now I'll give you one more example so that you can practically visualize these things. Let us say, shall we proceed? So अभी देखिए आप, just now you saw, as the velocity is increasing, the pressure is decreasing. What is the physical explanation for this? When the velocity is increasing, molecules are not getting sufficient time to exert normal force. That's why pressure is normal force, the pressure is decreasing. Good, my dear students. Very good. No problem at all. Not at all a problem. Now, one more thing. So I have I'll share it in a group. Amazing video which my student has done that experiment. I'll be sharing it in group. Don't worry. Now, देखो एक बार. One more example. Let us take sprays, DOs, spray. उसका example दूंगा. देखो, प्लीज अंडरस्टैंड केयरफुली. डीओ का एग्जांपल दे रहा हूं, सुनिए. नाउ आई विल प्रेस दिस. इसको प्रेस कर देना, इसको प्रेस कर देना, इसको प्रेस कर देना. व्हेन आई प्रेस, व्हाट विल हैपन? इधर देखो. व्हेन आई प्रेस दिस, द फ्लूइड विल मूव विथ हाई वेलोसिटी. सो वेलोसिटी विल बी हाई. देखो, जब मैं इसको प्रेस कर रहा हूं, तो नाउ प्लीज अंडरस्टैंड, व्हेन आई प्रेस इट, द फ्लूइड विल मूव विथ हाई वेलोसिटी. देखो, जब प्रेस कर रहा है, इसको प्रेस कर रहा है, द फ्लूइड विल मूव विथ हाई वेलोसिटी. सो व्हेन वेलोसिटी इज इंक्रीजिंग, द प्रेशर इज डिक्रीजिंग. तो यहां का प्रेशर कम होगा, यहां का प्रेशर ज्यादा है. हियर द प्रेशर इज मोर. एज द वेलोसिटी इज इंक्रीजिंग, व्हेन यू आर प्रेसिंग दिस, इसको प्रेस कर रहा है, इफ यू आर प्रेसिंग, द वेलोसिटी हियर इज इंक्रीजिंग. जब वेलोसिटी बढ़ रहा है, तो प्रेशर डिक्रीज हो रहा है. When pressure is decreasing, low pressure, low pressure से फ्लूइड आएगा and it will move in the form of spray. अरे यार, आर बी क्लियर? फिर से बता रहा हूं. When you are pressing, अरे यार, what is happening, my dear students? What is happening, my dear students? You are very weak. देखो, see, when I am pressing this, it will cause the flow of fluid. Velocity here is high. जब वेलोसिटी इंक्रीज हो रहा है तो प्रेशर क्या होगा? डिक्रीज होगा. जब प्रेशर कम हुआ, यहां का प्रेशर कम हुआ, यहां का प्रेशर ऑलरेडी ज्यादा है. वी आर नॉट चेंजिंग इट. हाई प्रेशर, हाई लो. From high to low, the liquid will rise. When liquid rises, when the spray rises, then it is coming in the form of a fine spray. अरे यार, are we clear? So मैं एक बार I'll share in group. अभी देख लेना. So I'll share right now in group so that you can visualize. 1 second, please. I am sharing in group. I'm sharing in group. अपने ग्रुप में देख लेना एक बार. Hope you got it. मिल गया? Please see in group. See in group. See in group. Please see in group and share. देखो, एक बार देखना. Please see in group. I have shared in group. I'm also watching. Are you watching? See, practically you have felt. आ गया? It clearly shows. हो गया? Seen na? Very good. Now come back. If you have seen, let's come back. देखो, तो क्या हो रहा है? Very simple logic. What a beautiful experiment. Actually, I asked one of my students to do and he has done. Excellent, my dear students. Very good. समझ गए? Is it clear? चले आगे बढ़े. और एक एग्जाम्पल ले लेंगे. We'll take one more example. देखो, we'll take one more example. Let us assume that थोड़ा हट के मजा करेंगे. Let's enjoy the class. थोड़ा मजा करेंगे. Come on. Are you ready? Very good. बोलो रे. See, शेख महबूब बादशाह क्या हो रहा है बेटा? शेख महबूब बादशाह. चलो सुनो. चलो एक बार देखेंगे. Are you ready? देखो, let us assume that थोड़ा enjoy करेंगे. Let's enjoy the class. Let us assume that you are going with your girlfriend on a long ride in a car. कार में जा रहे हैं. You and your girlfriend. You are going. Yeah. going in a car with all windows closed. Windows with a glass closed. And you are moving at 80 km per hour, आराम से you are going, you are driving. देखो, please see, you are going beautifully. Happily you are going. Suddenly your girlfriend asked, my dear. So her hair was loose, पूरा the hair was loose. मतलब छोटी वीटी कुछ नहीं, just western fashion, loose. Western fashion, loose hair, and she is sitting besides, adjacent to the driver's seat. So you are driving, and happily आप गाने सुनते हुए ओ मूड में चल रहे हैं. So suddenly she stopped the music and she asked, अरे possible है आदित्य possible है, अरे चलो possible है, चलो कोई problem नहीं. So now suddenly she stopped the music and she asked one question, my dear, are you mechanical engineer? Then you said, of course, I got 80% marks in my exams, I am the topper. Okay, good. Then she said, suddenly I lower the window, I open the window. Initially the window was closed, all glass was closed, pura pack closed. Then she said, suddenly I lower the glass so that the window is open, lower the glass. Then she asked, you said, so what is your question? Then she said, if I lower the glass, in which direction my hair will be blown? Will it blow outside or will it blow inside? मतलब glass जब open किए, will the hair be blown out or will the hair be blown in? This was the question asked. Now tell me, will it blow in or will it blow out? The question. Will it blow in or out? बोलो बोलो. Will it blow up, out or in? I am talking. Outward, 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 outward. Everyone is saying outward. Is it correct? Outward, outward. Okay, we'll see. See, my dear students. Outside, because inside pressure is very good, Nagaraju. So when the car is, let us assume this to be a car. देखो एक बार. You are sitting inside. Listen. You are sitting inside. This is the car. देखो. When the car is moving faster, this is, listen, no comments, please, no comments. The car is moving faster. So what is the velocity? When the car is moving faster, जब ये तेज जा रहा है, देखो, please comment मत करो बेटा. You are great students of India. Okay. When the car is moving faster, तेज जा रहा है, fast जा रहा है. So what is the velocity outside? Inside, it is stationary. देखो, windows पूरे बंद है. Inside, stationary. When outside it is going faster, the velocity is more. When the velocity is more, outside pressure is less. Inside pressure is more. Inside when the car is moving, bahar the velocity is more. When the velocity is more, the pressure, the normal force, when velocity is more, outside. When it is moving faster, the normal force will be less. Pressure is less outside. So inside the pressure is more. High pressure, low pressure, it will blow out. Such questions can be asked, and in interviews, if they ask Bernoulli's equation के practical examples, don't tell venturimeter, RFIS meter, pitot tube. Everyone will tell that. ऐसे questions दे देना, ऐसे answers दे देना. When they ask Can you give some examples of Bernoulli's? Then you say, sir, I want a piece of paper. Then they'll ask, please don't write and tell us, sir, I don't want paper to write, I'll do something. Then you will understand, he is going to do something. समझ में आया रे? अरे समझ में आया रे? आया रे बबलू? Very good. Very good. देखो एक बार. You should ask me one question. The question is, you should ask me one question. You should ask me one question. Sir, in thermodynamics, we have seen steady flow energy equation. What is steady flow energy equation? It is conservation of energy. What is steady flow energy equation? It is conservation of energy. It is conservation of energy. Then what is Bernoulli's equation? One second, please. What is Bernoulli's equation? It is also conservation of energy. Now the question that can come to our minds is, it is conservation of energy, it is also conservation of energy. It is for steady flow. Bernoulli's equation may also there is an assumption. What is that assumption? Steady flow. Now there is a confusion. Steady flow energy equation is applicable for steady flow. Bernoulli's equation is applicable for steady flow. Bernoulli's equation is conservation of energy. Steady flow is also conservation of energy. Then why do we need two? Very good, my dear students. Let us see the relationship between Bernoulli's equation and let us see the relationship between Bernoulli's equation and steady flow energy equation. Okay, please stop. Let me take steady flow energy equation. Let me take steady flow energy equation. Let me take steady flow energy equation. What is that? H1 plus C1 square. C1 in thermo we have taken C1 as velocity because velocity and volume both starts with V. So volume we have taken already V. Therefore in thermodynamics, to avoid the confusion between volume and velocity, I took C as velocity. But here I will take velocity as V only. No problem. Plus Z1G plus Q is equal to H2 plus C2 square by 2 Z2G plus W. Very good, my dear students. Can you tell me the assumptions for this equation? While deriving steady flow energy equation, only one assumption is made. The flow is steady. While deriving steady flow energy equation, only one assumption is made. The flow is steady. Now, my dear students, when number of assumptions are increasing, the usage of that equation will shrink. For example, if I make more assumptions, means you are putting so many limitations on that equation. So its usage will be less. Its usage will become less. Okay. Now understand carefully. Understand carefully, my dear students. What is that? It's something like this, I'm telling you. Tomorrow you want to marry and see your conditions. When conditions are increasing, availability will decrease. Conditions देखना. I want a tall girl. I want a fair girl. I want B.Tech girl. I want a girl with a salary of 1 lakh per month. I want a girl with huge father's property. She should stay in your state. These are the assumptions. Where do you find? So when conditions are increasing, its usage or availability will become less. So in steady flow energy equation, we made only one assumption, steady flow. If it is steady, remaining conditions we don't need. If it is steady, you apply. I said steady only. It may be compressible, it may be incompressible. It may be uniform, non-uniform. It may be viscous, non-viscous. It can be anything, but it should be steady. And now your conditions are, let us say you are going to get married. You say, I want a girl. Options are open. She can be BCom girl, BA girl, any girl. You said, I don't want, I am not interested in any salary, whether she is doing job or not. So your availability will increase. So in steady flow energy equation, only one condition is made. That's why its usage will be large. But now we'll see what is happening to Bernoulli. Look at, my dear students, Bernoulli, there are large assumptions, many assumptions. So that's why its usage is very limited. Though it is a conservation of energy, its usage is very limited. For example, अब देखना, this is my steady flow energy equation. अब मैं क्या कर रहा हूँ? Can I write enthalpy from your thermodynamics? Enthalpy can be written as U plus PV. Enthalpy can be written as U plus PV. अरे यार, H is equal to U plus PV. If it is specific enthalpy, specific interenergy, specific volume, plus V1 square by 2 plus Z1G plus Q is equal to H2 U2 plus P2 V2 plus V2 square by 2 plus Z2G plus W. Stop. Now this is only for steady. This is only for steady. Let me put more conditions. देखो, no work transfer. No heat transfer. No heat transfer. No work transfer, no heat transfer. Okay. Third. No change in internal energy. Now the equation will be P1. Can I write specific volume as 1 by density? Yes. P1, V1 is 1 by rho 1 plus V1 square by 2 plus Z1G is equal to P2. Specific volume is 1 by density. Specific volume is 1 by density plus V2 square by 2 plus Z2G. Now, incompressible. When I say incompressible, what will happen to the density? Rho 1, rho 2 will be same. So my equation will be, when rho incompressible, rho 1, rho 2 will be same. P1 by rho plus V1 square by 2 plus Z1G is equal to P2 by rho plus V2 square by 2 plus Z2G. What is this equation? Bernoulli's equation. Means in steady flow energy equation, if I make so many assumptions, I get Bernoulli's equation. So actually, which one is a bigger equation? Which one is a bigger? Either देखो, this is a steady flow energy. This is ये पूरा steady flow. ये पूरा, this is all steady flow. This is all इधर देखना. Look at, my dear students, all of you listen carefully. All of you understand carefully. 1 second please. देखो एक बार, I'll give you a beautiful picture, you don't have to worry. देखो एक बार, yes, don't worry, don't worry, don't worry, don't worry, let me explain very clearly. Yeah. So look at, so we made one assumption. We made one assumption. What is that? देखो एक बार, this is the region of steady. ये देखो एक बार, this is all steady, this is unsteady. ये बाहर का unsteady, बाहर का unsteady. So where can I apply steady flow energy equation? I can apply only in this shaded region. Now you said, अब क्या बोले? No heat transfer. No heat transfer. देखो, no heat transfer. Please look at, this is steady, but in this zone, there is a heat transfer. देखो देखो, in this zone, इसमें heat transfer है. Listen carefully, इसमें heat transfer है. So now tell the difference. देखो, this totally steady, this is no heat transfer, here there is a heat transfer. So I cannot apply Bernoulli's equation in this region. Why? Because there is a heat transfer, here there is no heat transfer. Now I'll make one more assumption. No work transfer. इसमें there is a work transfer, so here there is no work transfer. Next, incompressible. देखो एक बार, incompressible. This is compressible, this is incompressible. Means when assumptions are increasing, my usage of Bernoulli is decreasing. Means steady flow energy, if this is the steady flow energy equation, my Bernoulli is only part of this, So which one is a bigger equation, my dear students? Steady flow energy equation is a bigger equation. Bernoulli is very small equation. When assumptions are increasing, its usage validity will start shrinking. So please note on that. From steady flow energy equation, I can derive Bernoulli. I had actually derived Bernoulli from steady flow. From steady flow I can derive Bernoulli, but from Bernoulli you cannot derive steady flow. Hope it is clear, my dear students. Bernoulli is steady flow with so many assumptions.